Okay, finite state machine is, as the name suggests, a finite number of states, and we're going to use this finite state machine to transition between the states. The state is something like, maybe we're driving forward, let's say, or reverse, we're turning or rotating, rotate, maybe we are grasping something, some sort of action that we're performing, right, in our system. So say you have some sort of mechatronic device or an industrial robot, you're going to go grab this package and move it over. Well, grabbing the package, maybe sensing the package might be one of your states that you're doing. And once you have sensed the package and located it, then you're going to perform some action. So you could have in here, like sensing something. Okay. An event, we see an event as an instantaneous interruption to our code. So this would be like a Boolean reaching some value. So let's say you have a limit switch and you're performing some actions until the limit switch is actuated, and when it clicks over to the other state, you are going to do something else. Okay. So this is an event. Another event would be like an analog sensor reaching some set value. Wow, this is not working very well. Okay, so some set value. This would be like maybe you're moving this thing until you sense the wall is within such a distance, then you're going to stop, right? So either one, these two things can be written as a conditional statement. Like if the state of something changes, that's either true or false, then you could write an if statement about it, or you could say something like, if IR is less, IR sensor value is less than some distance, right? And then it will either be true or false. So this is kind of this Boolean effect here, where it's either a true or it's a false thing. One loop, your analog sensor is below the set value. The next loop, it's either at or above the set value, and now you want to perform some action. So the action is, we call this the service. Oops, I'm writing an S now. Action. So this is something like, maybe you're going to set a timer. Maybe you're going to run an actuator. Maybe you're going to reset something and do a counter, this sort of thing, right? And events and services go together. So when there's an event, we perform a service, and then we transition to a new state. That's how this works. So let's look at an example. I've written one out here. I've got this box. Let's just zoom in here on this box. I have this box, and I'm putting this mechatronic device inside of the box, and it has these 3 IR sensors shown in red. It's going to follow the wall on the right. When it reaches the wall in front, it's going to turn. So it'll turn this corner. It'll do it again. Keep going around. When it reaches this point again, after it's gone around one full turn, then it will, instead of turning, it will go into reverse and do the whole thing over again. Okay. So that's this robot running this maze here. Okay. So we have a state transition diagram that we're going to draw that will kind of graphically explain what we're doing. So here we're in the forward state. That's the state that we're going to begin with. And when we're here, we want to be able to go into turn when we reach the wall. And when we've completed a turn, we want to be able to go back into forward. Also, when we've gone around an entire circle, we want to be able to go, instead of turning, we want to be able to go into reverse. And likewise, if we're in reverse, we've gone around a full turn, we want to be able to go into forward. If we're in reverse, we also want to be able to say, hey, let's turn. We reached a corner. And if we've turned, we want to be able to go back into reverse. So here is our state transition diagram. We have transition arrows, and we have states in the circles. And in this case, every state can point to any other state. That's not always the case, but here we happen to have a unique situation where every state needs to be able to transition to any other state. Okay, so let's look at one or a few of these transition arrows. I'm going to write events in red and services in green. So here we're in the state, follow the wall. And if we have the turn counter is less than it was less than 4, apologize. If it's less than 4, and the IR sensor in the front is less than some value, then we know we've reached a corner and it's time to turn. So we're going to perform a service on that. We're going to increment our turn counter, and we are going to run our right wheel is going to go forward, and our left wheel is going to go in reverse. So this is, and there's one other thing that we're going to do. We also need to know when we've completed a turn, so we're going to get some encoder value. We're going to check to see where our encoder is, okay, something like that. And then, excuse me, we're in turn, and let's say we've reached this point where we have turned enough. Well, we have an event that takes place. So this would be like our encoder, it's reached some value, okay? And we also need to know which direction we're headed. So let's say we were going in forward, then we know we're going to come back along this transition arrow rather than along this one over here where we would go if we had been going in reverse. So we need to keep track of that, okay? And the service that we will perform here is we're going to run our right wheel forward and our left wheel forward, okay? Is there anything else that we're going to do here? Well, no, we've already incremented our turn when we transitioned into turn. And so we don't really have anything else to do here. If we were driving forward, we want to go back to driving forward again, okay? So we're just going to do that. And there you have it. Now, up here, our forward, we need to look at this other arrow that exits forward. This transition arrow is going to happen when our turn counter is 4. And we also need to see that the IR sensor is less than some value. Okay. In this case, we know that we've gone all the way around and we're seeing the wall again. And we know that this time, instead of turning, we're going to go into reverse. So we're going to set the turn counter equal to 0. We are going to put the right wheel into reverse and the left wheel into reverse. Okay. And that's our service that we're going to perform. Now you might say to me, well, that doesn't make any sense. These last 2 lines, why not just set the turn counter to 0 and go directly into reverse? Well, sometimes in this case, we have kind of a unique situation where the service that we're performing is identical to what exists, in here in this state. But let's say you were, rotating your industrial robot over to the conveyor belt, and the next state is to lower the arm. Well, then you would need to put in here, stop rotating, right? Because that's not going to be in the state lower the arm. There is no call to the rotational actuator in any way. So you would need to put it in here. So always write down your transitions here. Fill out your service. It doesn't take a lot to write this code, and it's good for you to be able to see in the transition from one state to another what exactly is happening. Now, in a state, real quick, we have the code that follows the wall here in this state. Whatever that is, it's going to read out the side IR sensor, and it's going to look at the front IR sensor. So I've got those here in this circle. Those are the 2 sensors it cares about. And it's going to do all the math it needs to do and figure out how to drive and follow the wall. Okay, all that code is contained within the state driving forward. Now, I don't have to look at the rear IR sensor, and I don't have to look at the encoders because they're irrelevant to me when I'm sitting here in the forward state. But when I transition to the turn state, I do need to look at the encoder. That matters to me now because I need to know, whether or not I've completed a turn. So the only sensor values that you need to grab are those which are pertinent to you in the particular state that you're in. I could continue filling this out, and I don't want to take a ton of time here, but you can see here that this, we're going to have something analogous there. We're going to have something analogous here. Analogous there. And this is going to have something analogous here. Just kind of the same song and dance in every one of these spots. I'm going to erase all this because it's getting kind of distracting. And let's move into one more thing here before I go on. We're going to talk about one other potential event. You're probably used to this. We have a situation here where we have some set value that we're looking to drive away from the wall as we follow along the wall. And we're going to start out here at some distance that's different from our set value. And we're going to follow this sort of path here. And at some point we get to this steady state value where we're more or less exactly the distance away that we want it to be. Within a percentage, right? We're going to kind of look at this and say, oh, it's, within 5%, 10% of where steady state is, and we're happy with that. And you could consider this to be an event. You could calculate it. You could say, hey, we've reached this point. So now that's an event, right? That's an instantaneous occurrence in our program. And we can perform some service and transition to some state. Since we don't care about it in our particular application, we're not going to look at this event. We're not even going to calculate it. We're not going to deal with it at all. It will happen, and we will just ignore it. If we did care, let's say we wanted to, hey, when I get to steady state, then I want to, I got to aim and fire something or, whatever, and I don't want to be like moving all around. So I'm going to wait till I'm steady state, and then I'm going to perform this action. Well, then we would care when it got to steady state. That would be an event for us because it would be a transition from one state to another, from the driving and following the wall into this fire or whatever. Now, another thing that's really beneficial about states is that I can have concurrent states. So let's say I had some sort of an arm on this little robot. It's going to pick up some package. Okay. Well, I can have the driving, maybe I would have another state here that would come out from any one of these would come out to this sort of, this state here, which is, like the grab the item state. Okay. And so at any time I'm going to be driving, I'll be turning and whatever, and I locate whatever object I'm looking for, and I could go into grabbing it. I could go pick it up. And I might need to stop driving forward, but I may continue driving forward. Let's say I'm driving forward and I need to, aim something and shoot a projectile. Well, I may want to still continue driving forward. So I can have this arm state over here. Maybe this is an arm state, and I can do something with my arm while driving forward. And in the arm state, I'm looking for some, event or service, and I'm going to I'm looking for some event. I'm going to do some service whenever something happens with my arm. So I can have concurrent states. I could be running, concurrently 8 different states, right? I'm sensing a package over here. I'm rotating at the same time. I'm also, computing some value to print something to the screen. So like formatting some sort of user interface screen or, whatever, right? I could be doing all of these things concurrently. That's the great benefit of having states. And state transition diagrams can really help to pictorially look at what you're doing and kind of decide how you're going to pull it off. So let's take a look real quick at what it would be to write some code that does these sorts of things. So I'm going to come in here. I've already written some stuff. Here I've set a string equal to state, and I'm going to set it to driving forward. So the value of state is driving forward. This is going to, we're just going to transition our states by changing the value stored in state. The nice thing about this is we actually have a word or sentence, phrase, or whatever that keys us into what state we're in. And it can be very descriptive because we can use however many words we need to explain that. We don't need like a super long camel case variable, right? So here in our void loop, we have our state. This is in this if statement. It's very easy to read. It's one of the benefits of using this kind of system. If the state is driving forward, then we're going to do crap, right? So this is the do crap stuff, right? And first thing we want to do is we want to get the sensor values that are pertinent to the current state. We want to perform the action of the current state. So this is the driving forward function where we get the value of we get the value here of the sensors that we care about. We're using them to drive forward and to determine then our event and service. So here's our events and service. The event comes here when the if statement is true. So if the turn counter is 4 and the front iris sensor is less than some value, let's look real quick at our transition diagram. So the turn counter is 4, and the iris sensor is less than some value. So we know that we're transitioning here into reverse, and we need to perform this service. So I'm going to set my turn counter equal to 0, and I'm going to drive in reverse. So let's look and see what we've written. So turn counter is indeed set to 0, and we're going to drive in reverse, and we set the value of state equal to driving in reverse. Next time through the loop, we're going to come in here and we're going to say if state is driving forward. It's not, so we'll jump down to if state is turning. It's not, we'll jump down to state driving in reverse, and that'll be true, and we'll execute whatever code is in that state. Okay. Otherwise, if turn counter is not 4, then it's less than 4, and we're going to come in here and we're going to see that the front iris sensor is less than some IR value, and this is going to be following this pathway. So that's this arrow. The turn counter is less than 4, so which means it's not going to go, this is not going to be true. So it'll go into this, and it will ask if the iris sensor is less than some value, and here's what we need to perform. We have to increment the turn counter, we have to initiate the turn, and we have to get an encoder value. Let's see where we are. So we get an encoder position, so we know when we've completed a turn. We increment the counter, and we turn on the code that turns us left, and we transition into state turning. Next time through the loop, turning is true, so we go in here and we execute the turn code. Just to real quick, we get the sensor values that we care about to turn, which is just here in this case just the encoder. If we were driving forward, we have some Boolean that we set to true when we're driving forward or false when we're driving in reverse. That's just kind of contained in this code or this code here. And we're going to run the turn left if we were driving forward. Otherwise, we were driving in reverse, and we need to turn right when we hit the wall. Okay. And then here is our events that we're looking for. So if our encoder is greater than some encoder value, and we were driving forward, we're going to go back to the forward state. Otherwise, we're going to go to the reverse state when we reach that encoder value. We were driving in reverse, we're going to go back to reverse. Okay. So this is a great way to deal with multiple states. And again, we can have embedded states, like multiple states running at the same time. Maybe in your void loop, you might have a switch case structure where you run multiple states at the same time in one case or whatever, right? Something like this. Another option here is this switch case, as I was talking about. We can use, instead of a string variable, we can use an integer, which is computationally less intensive. And we can use comments to tell us what state we're in. This is much better as far as the computational work that the compiler and program has to do, because the switch case is a lot faster. It just jumps to whichever case it belongs in. It doesn't have to ask all of the if-else questions. Where in the if-else structure, let's say you had 15 if-elses in a row, then it would have to ask 15 questions before it got to the last one and found that it was true. Okay. Where this one, it will just jump to the state. So this is faster, it's computationally less intensive. The code from here to there is identical to what we had in the other one. We're just, getting our sensor values, we're setting our turn counter and all of this jazz. When we change states, we just put a comment that lets us know which, because state is 3 doesn't mean anything to me. I tell it, yeah, we're going to transition to reverse state. So that's this code here. You might find this to be a lot more helpful, a lot of reasons to go this route versus the string route. Here's another option. Let's say you had some sort of robot here that's going to, as I keep going back to this, we rotate, we lower our arm, we grab a package, we lift it up, and then we're going to do something with it. We could use this sort of sequential way to tackle states. So we can have a state that's rotating. So while we're rotating, so this is some condition that says our rotational angle is less than our desired rotational angle. And we're going to get the sensor values we need again, and we're going to perform this rotate function. And when we get to the position that we want to be, this statement will no longer be true. Because here we're saying we're less than the rotational angle desired. So when we reach the rotational angle desired, we'll break out of this while loop. So when we break out, we know that the event has occurred. Because now, whatever rotational angle we've got to the one we wanted, so that's the event. We've reached the rotational angle we were desiring. So an event has occurred. We're going to perform some service here, and then we're going to go into the next state, which is lowering, and we're going to look at this Boolean value here to see whether our limit switch that says we lowered enough has happened, and we're going to get the sensor values, whatever we need in this case, reading that limit switch, and we're going to perform the action that we need to that's lowering. Okay, and just keep going through. We're going to grasp it, and then we're going to lift it back up. So this may be really helpful to you if you have kind of a sequence of things that you're going to do. Certainly, you can use any one of these structures to run a finite state machine, and you just have to kind of choose which one is more helpful to you. I want to say a little bit more about this one, even though it is more computationally intense. Imagine you have an industrial application where you've got some machinery and you have an operator running it. You have what's called a oh my gosh, I just forgot the name of it. You have a user interface. I don't know. I'm trying to think what the PLC version of that is. We have a user interface screen, HMI. There we go, human machine interface, and you want to let the operator know what the machine is doing so that they can, know whether it's actually performing it correctly or not, or whether they want to stop it in the middle of some operation. So you can have this state printed on your HMI. And it'll say, it's, pressurizing the system, it's bleeding it off, it's, doing whatever. And they can determine, oh, hey, I don't want to stop the machine and shut it down yet because it's still pressurizing. So let's wait till that's, depressurized before we, pull the plug on it or something. Or if it's malfunctioning, it's really nice. This makes it really easy to troubleshoot. I just need to print state to the screen. And when I have something going weird, I just look at what state I'm in, and then I know I need to go to that block of code to fix it. So if something went weird and I'm driving forward, I know that my problem is located here. Of course, here I'm calling this function, this drive forward function. So I may have another place to go look for an error, there. But it does narrow it down for you. I think this becomes really, really helpful in that way. And also it's really easy for the people to read it. Again, commenting your code, if you do a really good job commenting, you can get this to work as well. So I hope this has been helpful.